Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the awesome stuff. This is the AAS Journal Author Series. And I am super happy to have Mark Phillips with us today. Hey, Mark.
Hey, Frank. How you doing?
I am doing awesome on this Valentine's Day. February 14th is 2020.
Valentine's Day.
Yeah.
I got my wife flowers.
Well, you're doing better than I did. I'm in trouble. I should get something. Very cool. Very good. And Mark, where are you located at? Where's your wave function these days?
Well, I live a fair fraction of the year here in Chile, so I'm coming from my office at the La Serena headquarters of Las Campanas Observatory.
Very cool.
La Serena, Chile.
Very cool. So we're doing a halfway around the world Zoom adventure here. It's very cool. Mark, do you surf?
I know everybody always asks me that because I wear these.
You got a Quicksilver shirt.
No, my daughter gave me this one.
Very good. Very
no,
good.
I play golf, which is not nearly as exciting.
Yeah, or at least it's a little slower than surfing is. So let's put it that way. Very cool. Very cool. And Mark, what do you like to do for research?
Well, since the late 1980s, I've been working almost exclusively on supernovae and mostly on type 1A supernovae, although I did do a lot of work on 1987A as well.
Indeed. Very cool. And that is going to bring us to this very awesome APJ article. It's open access, people, so you can go get a copy for free. Go grab a copy. The absolute magnitudes of 1991 T-like supernovae. And Mark, take us away.
Okay. Well, first of all, you can see there's a whole bunch of co-authors here, so I need to give full credit to them. These are the people that contributed to this paper who were in our Carnegie Supernova Project team. Carnegie Supernova Project started in 2004. Seems hard to believe, 19 years ago.
Time flies.
And this is a topic that's sort of dear to my heart because back in 1991, when I was getting interested in type 1A supernovae, supernova 1991T appeared, and it surprised us all because it was a bit different than what we call quote unquote normal type 1A supernovae.
Yes.
And so I've always had in the back of my mind that I'd like to study these objects in more detail and try to understand if they're part of the normal type 1A supernovae, which go from fairly low luminosity objects to the higher luminosity objects, which are the 91T-like objects, supernovae. So this is something that with our CSP data that we can look at. And, type 1A supernovae are important. They're important for their contributions to metallicity of the galaxy and universe. But they also have been used, in the last 20 years, they've been used for cosmological studies and been very important. So understanding the absolute magnitudes of 91T-like objects is important if we're going to use these objects in cosmology. Right. And we probably will have lots of these objects in cosmology, at least some of these objects, because they're the most luminous ones. And the further out you go, you're going to have higher contribution of these objects. Indeed. So that's sort of the background of this paper. I think most people know that type 1A supernovae are not perfect standard candles. They do range in luminosity. And luminosity, fortunately, is related to the width of the light curve, or the decline rate from maximum of the B light curve. And if you take this into account, sort of like we do with Cepheids, using their periods to get their luminosities, then you can determine distances to 5 to 10% with type 1A supernovae.
Nice.
But as I said, 91T is one that often people refer to it as peculiar type 1A supernova. So why is it peculiar? Well, basically at pre-maximum and even at maximum, the strongest lines that it showed were iron 3 absorption lines. Whereas a typical type 1a supernova at maximum shows lines of silicon 2, calcium 2, and sulfur 2, so lower ionization. So that they're quite different at before and at maximum, but by 2 weeks after maximum, they actually evolved to become very similar to that of a normal type 1a supernova. Their spectra evolved that way. And so if you don't catch them early, you can certainly confuse them with a normal type 1a.
Yeah.
I really don't like this word normal because it sort of implies that 91Ts are peculiar. And as I think I'll show here, I believe they're just the high luminosity end of the sequence.
There you go.
So when 91T appeared, turned out people got a Cepheid distance to its host galaxy and tried to calculate how bright it was. And the conclusion was that it might be as much as a half magnitude brighter than typical type 1a.
There you go.
But unfortunately, the error in the distance modulus was large enough that that 0.5 magnitudes had an error associated with it around 0.5 magnitudes. So not particularly definitive.
Right.
So in 1995, there was this paper by Peter Nugent, and I collaborated with him on this, David Branch and others. And what Peter, I had given a poster at the AAS meeting actually, showing that the sequence in decline rate and in luminosity of type 1a supernovae was accompanied by changes in the spectral features. The fastest declining, lowest luminosity objects actually showed titanium absorption at maximum. That disappeared by the time you got to the typical type 1As. And also the ratio of the two silicon 2 lines, the 5972 and there we go, that's good. 5972 and 6355. We look at this first graph, we might as well go to the spectra.
Okay.
And the Nugent et al. Paper basically said, okay, we can recreate this by just artificially increasing the temperature in the outer layers of the supernova. And in fact, we're able to show that you could go all the way from the 91BG-like objects, which are the low luminosity fast decliners, to the 91T-like objects. And this presumably is due to the amount of radioactive 56 nickel that's produced in the explosion and how it is distributed out into the outer layers. So this first figure, if we look at the top part, these are spectra of 1991T, and then the bottom spectrum, the black one, is 2011 FE, which is the canonical type 1a supernova. And you can see the huge difference between the two spectra at this stage. The iron 3 lines in the upper, in the fuchsia colored, magenta colored spectrum, iron 3 lines are very strong. They're actually there in 2011 FE, but iron 2, magnesium 2, silicon 2 are much stronger. And then over at the position of the silicon 2 6355 line, you can see there's nothing there basically in 91T, whereas it's the strongest line in the spectrum in the normal type 1a.
Right.
And the two spectra in the middle are objects that are somewhat intermediate between these two. Let's stay in that upper panel first.
Upper one? Okay. Oh, the green and brown lines. Yep.
Right. The green and brown, or blue and brown, whatever they are.
Yeah.
The greenish bluish one is an object called 99AA, which in fact looks to be somewhere in between in the strength. It has silicon 2, but it also has very strong iron 3.
Yes.
It looks between 91T and 2011 FE. The brown spectrum is 1999 EE, which looks pretty similar to 99 AA, but it also has features that you see in the 2011 E. Plus, it also has high velocity silicon-2, which sort of, that's not the topic of this paper, but some of these objects do show this high velocity silicon and calcium early on. So if we go to the middle panel here, these are spectra around 2 to 3 days before maximum. So that first one was 8 or 9 days before maximum. The second one is getting close to maximum now. And you can see there's a progression between the 4 supernovae in the strength of the silicon-2 line, and also in the strength of the iron-3, which is strongest in the 91Ts, weakest in the typical type 1A 2011 FE,
right,
and the silicon-2, which is strongest in the typical type 1A, and you can now see it in the 91T.
Yes, starting to depth.
And then if we go to the final panel here,
Post.
This is now roughly 2 weeks after maximum. And now we see the spectra are very, very similar over most of the spectral region. The silicon-2 line is still a bit weaker in 91T, the silicon-2 6355. And calcium-2 is maybe, H and K is maybe a little bit weaker, but to the trained eye, you have to really be careful to say that you could actually classify something as a 91T as opposed to a typical type 1A at this point in time.
At this one, yeah, right. Okay.
Okay. There's one other thing I wanted to point out in this figure. If we go back up to the first 2 panels, I want you to notice that the spectrum of 91T that is, let me get this right here. The spectrum of 91T that we see in the middle panel and the spectrum of 99AA in the upper panel actually look very similar.
Okay.
The strength of the calcium is very similar in them.
Yeah. Okay.
Okay. And the and the strength of the silicon-2 as well. So you could easily misidentify a 99AA-like object and a 91T-like object. So to differentiate between the two, you actually need to know the light curve phase. Okay. And I'll show you this in another graph in a second or two.
Okay.
So
cool.
Okay. So we can now, I think people have an understanding of what the spectral differences are between these different kinds of objects. And if we want to study these objects, 91T-like objects, we have to find them. We have to be able to identify them.
Indeed.
So as I just said here, we do need to have an accurate light curve phase. So that means we have to have light curve photometry in order to have that estimate. And it turns out that the way we're going to want to use this is by the way we're going to identify these objects is through the feature that changes the most, which is the silicon-2.
Yes.
Okay. So if we go down to the next figure.
Okay, let's take a look at this.
This is called a branch diagram in the supernova circles. After David Branch, some papers that he was the first author on. And what David did was he used the strengths of the 2 silicon-2 lines, 5972 and 6355. So these are what we call pseudo-equivalent widths. We call them pseudo-equivalent widths because you don't really know where the continuum is in these objects.
Okay.
But we measure them in a standard sort of way. And he divided this diagram into 4 different parts. The CNs, which are the black circles,
yes,
are what he called core normal type 1As.
Yes.
And these are what we call normal, typical type 1As. You can see that 2011 FE falls right in the core normal group.
Yes.
It is, as I said, it's the one that everybody compares to now.
Poster child.
So well observed, exactly. If we look at 91T over here, it's in this area called the SS, which is shallow silicon.
Okay.
Okay.
Yes.
Makes sense?
Yes.
And we actually see 99AA is also in the shallow silicon.
Right.
And 99EE is right on the edge between the core normals and the shallow silicon. So they form this sequence. The other two types that you can see in this diagram are the CLs, which are the red diamonds. They're called cool. You call them CL for cool. They're the fast declining low luminosity objects like 91BG.
Yes.
And then the BLs, which are the blue upside down triangles, these are broad lined objects. And these tend to be associated with what we call the high velocity type 1A supernovae. There's some supernovae that at maximum light have much higher velocities than normal. Again, this is something David Branch pointed out back in the 80s. Now, the divisions between SS and CN and CN and BL are pretty, they're not obvious. There has been some work by our group where we've actually looked at this, and you could argue that they do form groups, but as to exactly where you draw the borders, it's not so trivial.
Yeah.
Okay. Now, if we want to find 91T-like objects,
okay,
and I should have said at the beginning, these are based on a spectrum at maximum light.
Yes.
Okay. To do a branch diagram, you have to have a spectrum at maximum or within a couple of days of maximum. Then, we just look for objects that fall over where 91T is.
Yes.
Basically have almost no measurable 5972 and weak 6355. The problem is that not everybody gets a spectrum at maximum light of a particular supernova. In fact, oftentimes nowadays with the searches that go on where they find the supernova very early, you get a very early spectrum. And they take this, say it's classification, and many people don't even take any more spectra because they're more interested in using them for distances.
Right. Okay.
Okay. Now, let's look over at the right-hand side of this figure, and can you keep the left-hand side in at the same time?
Sure,
please?
I can. Let's do this.
Just make it, that's right. Now, this diagram actually looks a lot like the SSCN part of the branch diagram.
Yes.
And you can see it's got the same x-axis, which is the pseudo-equivalent width of the silicon 26355 line. And it also, but the y-axis, instead of it being the other silicon 2 line, it's the decline rate. This is the amount in magnitudes that the supernova declines in its B-light curve the first 15 days following maximum light.
I'm with you.
Delta M15B is what it's called. And so this is, we're using the decline rate here. Well, it turns out the decline rate correlates quite strongly with the 5972 silicon 2 line. So that's why these two diagrams look so similar.
Nice.
But the thing that I wanted to point out here is that you notice that the 99AA objects, which are the triangles, excuse me, let's call those SS objects,
right?
To the triangles here, and the core normals, the black circles, and 91T all have very similar decline rates. So the decline rate cannot be used to identify these objects.
Right, not real crisp.
No, not at all. So in fact, what I'm going to do in the rest of the paper is I'm going to use these data are all taken from the Carnegie Supernova Project, the second version of it, and I'm going to use all of these SS objects and all of the type 1, the core normals that have decline rates less than 1.1 magnitudes, which is the red line in this figure.
Got it.
And I'm going to compare those objects.
Okay.
So throw out the core normals that are at the top. Okay.
I'm with you.
All right, so we need to find a way to identify the 91Ts that if we don't have a spectrum of maximum light. So if we go down to the next figure.
Identifying 91T likes. There we go. All right.
Okay, we look at the left-hand side here now. Here again, we have the black diamond. In fact, is 2011 FE. This is the pseudo equivalent width of the 6355 silicon 2 line as a function of light curve phase. So as a function of with respect to B maximum light.
Right.
And the dashed lines, black lines, are just a whole bunch of core normal type 1As that we're using for these purposes from spectral studies by people.
Got it. Okay.
Okay, and then the diamonds are 1999 EE. The cyan colored squares are 1999 AA.
Okay.
And the magenta circles are 91T. So you can see that not just at maximum light, but in fact before maximum light and out to about 10 days after maximum light, 91Ts always have a smaller equivalent width of the silicon 2 6355 line than do the 99 AAs and the core normal.
Right. Okay.
And so, in fact, we don't need the 5972 line of silicon 2. We can measure the 6355 line equivalent width, and as long as we have an accurate estimate of the epoch of B maximum, we can then put the point on this plot.
Right.
Now, what you see here, what I see here is it's a pretty smooth continuum. One of the things that's striking in this figure as well is that the core normals oftentimes start off with very high equivalent widths of 6355 at the earliest epochs.
Right.
And that is this high velocity component that I pointed out in 99EE.
Oh, yeah. Okay.
That is not visible in the SSs. If you look, there's a few SSs that go, they've been caught early, and you don't see this behavior there.
Right.
So we don't really understand, well, some people think they understand it, but I would say that there's not consensus on exactly as to what the high velocity component is due to.
Indeed.
But there's a difference, there's a clear difference in that we don't see it to be strong at all in the SSs, whereas you do see it to be strong in the core normals.
Yes.
And it's either an ionization effect or something else going on here.
Okay.
I'd be inclined to think it's ionization just because the spectra of the 91Ts and 99As have this very strong iron 3.
Right, which is
okay. One other thing to notice in this, they apply to two other supernovae. There's 2005 HK, which is what we call an O2CX-like. Some people call them type 1 AX.
right.
And these are objects that we're still finding out a lot about. The thinking, I think, currently now is that they're pure deflagrations where the progenitor white dwarf is not completely destroyed. But for this diagram, they fall very close to where the 91Ts are. So they're a possible source of contamination.
Right.
However, they have very different I band and infrared light curves. And so if you get very good photometry that includes the I band or near infrared, you can see quite a strong difference in these objects. The typical type 1A shows a secondary maximum in I and also in the near infrared, whereas these O2CX-like objects just show a very broad maximum, and that's it. So light curves are very important for eliminating them. The other objects that can also confuse are the the O3 FG likes.
Right.
Some people call these super Chandra objects. I don't like to use super Chandra because I think it presupposes that they're super Chandra mass. I don't think we know that. So we call it after the first to be identified. Again, the I-band and near-infrared light curves of these objects are also quite different than a typical type 1A. So that's the way we can weed those out. There are also different luminosities. The O3FG-like objects tend to be very luminous, whereas the O2CX-like objects tend to be less luminous.
Correct. Yep.
Okay. If we look at the right-hand side of the figure real quickly here, just real quick, instead of, we could, if we want to get rid of the light curve phase,
okay,
we could use the two strengths, the calcium 2 and the silicon 2 equivalent widths. If you remember the 91Ts, both calcium and silicon were very weak.
Yes.
Whereas in regular core normals, they're quite strong. And you can see the evolution of 91T in this figure. The numbers correspond to the phase with respect to B maximum. And the 91T is very clearly, if you see an object that has almost no silicon and almost no calcium 2, and it's very early in its light curve, it's a 91T. But you can see this region of overlap where you can confuse a 99AA with a 91T if you don't know the light curve phase. So important to know the light curve phase if you want to have a pure sample of 91T like objects. Okay, cool. Yeah,
I'm with you.
Okay, so all right. So what we did is in this paper is we took the CSP2 sample, which is around 214 type 1A supernovae, and we searched for the 91T like objects. Okay. We only found 10. Well, so not particularly abundant in this sample. There, in future work, which I'll discuss later, would be trying to determine actually from a better sample, a nice sample from one search for a search, for example. You could try to determine how common they are in the local universe. So that's something to do in the future. Cool. So we found 10. Okay, and 10%. That's right. If we go to the next figure, it is 10%. That's right.
And the CS2 sample,
it's a somewhat higher fraction of the luminous side. So if we go to this figure here, these are all of the supernovae, the 10 supernovae we found. I've interspersed some spectra of 91T just so you can compare them. At the early times, there's more of a variability in the strength of the iron 3 features. You can see that this CS130303 with a long name object, also Ogle 214, supernova 141, and then the next one down, Assassin 14KD. They all have fairly weak iron 3. Their light curves are very similar. Okay. Whereas some of the other ones, if we look at 2014 DL, has very strong iron 3 at first. This is an interesting question as to what this variability of the strength of these lines might be due to. In the paper, we speculate maybe it's an abundance effect, since at the very early epochs, the nickel hasn't had time to decay to iron, so you're seeing primordial iron basically in the outer layers. Okay. But it could also be due to other things. For example, there could be circumstellar interactions, so producing a continuum. So that's another future area to try to trying to understand the physics of these objects. But you can see the spectra are all pretty similar to the 91T in the evolution and the like. We continue now to the bottom line for the paper, which is the next figures.
These things are telluric?
Those are that's right, they're telluric features.
Okay, not removed. Okay, gotcha.
Yeah, I mean, some people remove them, some people don't.
It's all good. All good. Just checking. Figure 5, Hubble diagram. Woohoo.
Yeah. Okay, so here we plot in this first figure the delta in the distance modulus. So we've taken the whole 214 supernovae in the CSP and fit the Hubble diagram for them. These are all, I should say, it's not the full sample 214. It's a somewhat smaller number that are redshift 0.02 or greater.
Okay.
So that peculiar velocities are not a significant fraction of the heliocentric velocity.
There we go.
So we fit fit a Hubble diagram, basically a cosmology model, with including dark energy and the like. Although these are very nearby, relatively nearby, so it's not a huge effect. And you can compare then the distance modulus that you would get just taking the heliocentric velocity, or it's actually not the heliocentric velocity, it's the CMB velocity.
There you go.
We're using. You compare that with the distance modulus you would calculate based on the brightness of the supernova. Okay, so you use a program like what we use is Snoopy, which was developed by Chris Burns, who's a member of our group. And so you run the photometry through Snoopy, and it knows what the redshift of the object is, and so it knows the luminosities. Okay, it also uses colors of the supernovae to determine a host galaxy reddening, correct for that, and you end up with a luminosity, and you then assume it's got the luminosity of an object of the same decline rate, basically, and that therefore gives you a distance. Okay, it's a distance based on luminosity, not a distance based on redshift.
Right.
And so that's what the delta M minus M is, M minus capital M. The Hubble residual is what it is.
Yes.
Okay?
Yes.
And then we plot that versus the decline rate, delta M15 here. And again, the 91Ts are the magenta triangles, the 99AAs are the sort of cyan colored triangles, and then the open black circles are the branch CN. These are all the ones with decline rates of 1.1 or less. And you can see that the 91T likes are more luminous as a group than the CNs and the SSs. But you can also see what we saw earlier, which is we can't really use the decline rate to predict what these Hubble residuals should be.
Right. It was a little
So if we go to the figure on the right, we're now using the way that we found these objects, which is the equivalent width of the silicon 2 line. The way we've identified them is through the strength of it at maximum light, roughly.
Yes.
And if we plot that versus the Hubble residual in the top, now we can see that they separate out very nicely.
Very nice.
And in fact, at least when I look at this diagram, what I see is a more or less continuous a relationship between them, with the 99AAs being maybe slightly more luminous than the core normals.
Yeah.
And the 91Ts being significantly more luminous in general. So something like 0.1 to 0.5 magnitudes more luminous. This is more luminous with respect to a supernova, the same decline rate, remember.
Right. Cool.
Okay.
I'm with you.
Now, the one concern we have here is that, like I said, if we use Snoopy, Chris Burns' program, he's assuming a color model, which is actually a function of decline rate for the supernovae, in order to determine the host galaxy reddening. And if we look at this, the bottom part, these are the reddenings that have been determined as a function of the silicon equivalent width. And we can see that the 91Ts have a somewhat higher group reddening, I'd say, average reddening than the SS, the 99AA likes. On the other hand, the core normals, it's a bit higher, but not that much higher than the core normals. But if you remember, this program, Snoopy, assumes they all have the same colors.
Okay.
And that's probably not a bad assumption to first order, but they clearly have somewhat different spectra at maximum, and the spectra will have some sort of an influence on the color.
Of course, absolutely.
Probably not a huge one, but we don't know. So the one thing we wanted to make sure that we can believe this upper diagram here is to try to look at this as a function of wavelength. So here we're using all of the information from the photometry. CSP2 took UGRI, BV, YJH light curves.
Yes.
So going from the optical UV to the near infrared.
Yep.
And as we know, the optical is much more susceptible to reddening, to extinction by reddening than the infrared. So we can look at this as a function of wavelength, a function of filter, and that's the last of the figures that I wanted to show here.
Let's take a look at figure mean values. Very good. Conclusions. Okay.
We can come back to the table here in a second.
B-band Hubbles. There we go. Okay.
Right. So here, what I've done is we've plotted the Hubble diagram residual in V versus B in this diagram, in R versus B in the one at the right side, upper right, and Y versus B in the lower left, and then H versus B in the lower right.
Okay.
And these, you can see there's very good correlation. If looking at this, in all 4 diagrams, the 91Ts have the most negative residual.
Yeah.
It implies that they are not just overluminous in B, but they're overluminous basically in all of these colors. Now, the concern here would be, okay, but we're using in Snoopy a color model, which assumes that they all have the same colors.
Yes.
And so what if we're making a mistake and we're deriving incorrect values of the color excess, for example?
Okay.
So the beauty of these diagrams is you're mixing different wavelengths, basically. And so if we look at the upper left diagram, I plotted a dashed line and excuse me, a solid line, and that solid line is what we would get if we had a plus or minus a half magnitude error in the color excess, and multiplying that by R sub B. Okay, the R. In order to find out how much extinction, you have to multiply by the R plus times the color excess.
Yes.
And you can see here that if you were making an error in the color excesses of plus or minus a half magnitude, it doesn't make much of a difference here in V and B. Right. But if we go to the lower right corner now,
ooh, that makes a big difference.
It makes a huge difference, and that's because the H band is almost transparent to dust. And so, if you make a big error in the color excess, it doesn't make much difference in the amount of absorption, whereas it makes a big difference in B. So if this correlation that we're seeing here were due to making mistakes in reddening, we would expect that in this diagram that it would not be a 45-degree line to correlation.
Right.
And in fact, what is this correlation due to? It's due to peculiar velocities. It's due to the peculiar velocities of the supernovae themselves. And you can derive when we fit for the Hubble diagram, you can actually derive what the peculiar velocity is that produces these effects. And we get typically 350 kilometers per second.
This line rolls over as you move toward the red, right?
So hopefully that's clear.
Yes.
So I think this is pretty good evidence that, yes, that we may be making small errors in the
color model.
In what we derive for the color excesses from Snoopy, but they're not what's producing this effect. We can pretty clearly conclude that 91Ts are more luminous, and they're more luminous at all of these.
All the bands. Yep.
That's right.
Yep.
Okay, that's basically the bottom line. So, using this CSP2 sample, I think we're able to definitively show that the 91Ts, which are the extremes of the type 1a supernovae, they are more luminous. And the other thing we're able to show is that decline rate or light curve width alone does not allow you to separate these objects from core normals and 99AA-like objects that have the same sorts of decline rates. And so you do have to take this into account when you're using these objects in any kind of cosmological study for these most luminous objects.
Right.
So the areas that we need to go further in understanding these objects are, first of all, are they truly just the most luminous end of the luminosity decline rate relationship, or let's say just the luminosity relationship of type 1As? I think most of the evidence certainly points yes to that, but there is a very curious fact, which is there's a kind of type 1A supernova called the 1A CSM.
Yes. And
there's only a few examples of these, but one or two of them, very early spectra showed a 91T-like spectrum.
Oh, no.
And in one case, it took something like 20 or 30 days. It evolved as a normal type 1A supernova. And then all of a sudden, the ejecta hit circumstellar material. And the spectrum changes completely. It becomes more luminous, the object. So that's sort of disturbing that these things look like 91Ts.
Unfortunate.
But it's possible that all 91Ts have some circumstellar material associated with them, and that these type 1A CSMs are simply the ones where the material is closer to the object.
Okay.
And in fact, there is a paper out there where a number of years after a type 1A went off that was suspected of being a 91T, a circumstellar interaction is seen.
Ooh,
so
cool.
So if they are the at the luminous extreme of type 1As, but otherwise normal, then maybe we should also be looking for circumstellar material around core normals.
Exactly.
So it's an interesting question, and I think it's another reason for continuing to study these objects, particularly getting not just the early epoch data, but following them for as long as one can.
As long as one can. Absolutely. You want to say something about table 1 in the appendix?
Yeah, sure. In the appendix, we
go to the appendix.
Just wanted to, we look at the table first.
Okay.
The table, yeah, no, it's okay. Go to the table.
Table.
Yeah, the table just summarizes the mean values that we get for, first of all, for decline rate, and also for the host galaxy reddening, color excesses, and finally the Hubble residuals. And these are for 91T likes, SS, which would be the 99AA likes in this case, and CN. And the N's are the number of supernovae in each group. And we can see that the mean value for just the last row is around minus 0.33 magnitudes in terms of being over bright, the 91Ts.
Yes.
The 99AAs, the SSs are around 0, and there's maybe very slight evidence, although certainly within the errors, the CNs and the SSs are the same, but maybe slight evidence the CNs are maybe just slightly dimmer. So I would say the conclusion is CNs and SSs look to be very similar. 91Ts are clearly brighter.
Yes. Okay.
And then the appendix in the appendix, we just go through the 10 91T-like objects. We just look at this this graph here.
Yeah, let's look at this one. Okay.
And this is how you use this this diagram. Again, I've put the 91T on there again, and 99AA, their evolution, just to show how they evolve in this diagram of the 6355 pseudoequivalent width versus light curve phase. And then the points are just correspond to the 10 objects that we discovered that fit the 91Ts.
Cool. Little variation, but it's okay. Very nice. Cool. All right, Mark, I want to thank you so much for walking us through your very lovely hunt for 91T articles. Very cool. So you mentioned it a little bit when we were talking through it. So let me push on a little bit. So where do you think we go over the next 2 to 5 years on this? Are there going to be additional observational campaigns to, instead of Carnegie 2 having 125 objects, maybe we get 1,000 objects? Some of the new telescopes going up, can some of those help? How about some of the models? What needs to be done on some of the models? Maybe the models to going in Snoopy, for example, those kind of things. So where do you think we head on this hunt for 91Ts over the next couple of years?
Yeah, well, I think, first of all, I mentioned earlier, it would be very nice to know what the actual, frequency of this kind of 91T-like object is in the local universe.
Indeed.
The CSP2 was a follow-up program. It was not a discovery program. And so the CSP2 mostly came, the supernova mostly came from blind surveys, untargeted surveys.
Okay.
And we're seeing something like 10% of the objects, 5 to 10% are 91T-likes. But much better would be, some of the search programs, for example, ZTF or others who've got very large numbers of these objects, where you could use these diagrams to identify the 91Ts and then calculate a much more precise value for their frequency. I think we also need to understand how these are produced, not just the physics, but what the progenitors are. And our group, our CSP2 group, we're looking at the CSP2 sample, and we have first of all, we have extensive photometry. We have also, through our collaboration, we've gotten spectra of the host galaxies, and in fact, in the spectra around where the supernova appeared. And we need to look and see the evidence so far that's published is that these 91T-like objects are associated with star-forming galaxies for sure. But most type 1As are associated with star-forming galaxies. But are they somehow different, or are they very similar to the core normals and the 99AAs and the like? So we'll be doing that, and then actually trying to understand the explosion mechanism, the progenitor explosion mechanism. And I know my colleague Peter Hoflich, who's part of CSP, has lots of thoughts on this, and I'm trying to put together a paper summarizing all of our photometry and these other data, and then handing it over to Peter. And we have another couple of theorists in our group as well, and say, let's try to come up with what's a best scenario for how you produce these objects. Right. So
yay.
that's what the plan is. We'll see.
Cool.
I'm retired now, so we'll see how much energy I've got.
Well, we're gonna have to coax you out of retirement there, Mark. We're gonna have to coax you out. Oh, very cool. Very cool. Well, I really look forward to seeing this hunt for 91Ts and how many are in the local universe. Just moving forward over the next couple of years, it'll be very cool to see. I'll find a number of these. So very nice.
Great.
Mark, I want to thank you once again for walking us through your very lovely article.
Well, thank you. It's been fun.
And that'll do, everyone. And I hope this made your astronomy day just a little bit better, and we'll see you on the next one. Bye-bye.